Anybody is there?
Yes, ma'am.
Okay. So, in the last lecture, we have seen that when a plane wave is moving and it strikes the boundary, because waveform is not always conducting in the homogeneous medium. Okay, it will be traveling, it will be propagating in the non-homogeneous medium. That means it is changing one medium to another. It may be changing the medium from dielectric to conductor, or dielectric to dielectric with different parameters like value of epsilon, mu, conductor to conductor, right? So there may be non-homogeneous media. So we will see now what when this waveform strikes the boundary of two media. It may be the same media, it may be the different media. Okay, so yesterday we have started. So this is the we have considered in yesterday's lecture. I have shown you. So this was our first medium, and this was our second medium. This was the first medium, this was the second medium, and this is the boundary. So at this boundary, the wavefront which is coming from medium 1 strikes the boundary of medium 1 and medium 2. So let us indicate the incident wave as with suffix I, electric field, incident electric field with suffix I, and incident magnetic field with suffix I. Okay. Now you know that electromagnetic waveform uh, is made up of electric and magnetic field, both E and H field, and they are traveling in both E and H field are perpendicular to each other, right? And this waveform is traveling in a direction which is again perpendicular to both of them. So we will represent the electric field and magnetic field separately. We'll represent the electric and magnetic field differently. So this is EIS, indicate incident electric field. HIS indicate incident magnetic field. How you will represent a field which is traveling in a Z direction? So let's take its amplitude EI0, and it is traveling. So we used to represent a waveform as e raised to minus gamma Z. What is gamma? Gamma is a propagation constant. You know, whenever waveform is moving, its propagation constant indicate that there are some losses taking place when the waveform is propagating. What are that losses? What is gamma equal to? There is sigma, there is attenuation constant and phase constant. So attenuation is alpha. Attenuation alpha is happening and phase reversal is also happening. So in all, we treat it with the propagation constant gamma. So we will represent the incident electric field by EI0 e raised to minus gamma 1 Z, where this indicates the amplitude. And this amplitude, so you use to indicate gamma as a propagation constant. If it's a forward traveling wave, it will be minus gamma. If it is a reverse traveling, it will be plus gamma. So this way, some part is transmitted, some is reflected back. Now, if you want to visualize how this field are appearing, you can assume some axis XYZ. So let your E field be along X axis. Let your E field be along X axis. So this is the E field. When it moves in the, when it transmitted in another, according to boundary condition, it is continuous. So same direction will be there. Now this is H field shown along Y axis. So it will be again maintained same in the reflected portion. Waveform is moving along Z axis. It is moving along Z axis. After reflection, if you find this was E field, now it is reversed. So this is your E field which is reversed. Okay, E field is reversed. Fine. Similarly, if this was your H field is also reverse because it is reflection. Reflection is happening. So the same thing is shown here. This is the direction of E field. This is the direction of H field. So this is incident wave. This is transmitted wave and this is reflected wave. Now for every medium, we have already defined some parameters, sigma 1, epsilon 1, mu 1, eta 1. Similarly, here also conductivity, permittivity, permeability and intrinsic impedance for second medium is given. Now we will denote here EIS is the incident electric field and it is in this direction, X direction. This is your X axis. This right side is a so this is X axis. This is the direction of propagation Z axis and one which is perpendicular to this, one which is perpendicular to this, you can imagine that it is coming out, it is coming outward at your end. So from this point you can imagine this wave form is coming towards you, outward. So this point is indicated by a dot. So dot indicates the direction is outward. So if this is a plane, so this waveform is projecting outward. It means E and H are perpendicular to each other and this is the direction of propagation. If this wavefront is moving in inward direction, we will indicate by this by a cross. We will indicate this by a cross. Okay. So incident wave, this is the direction of propagation and H is denoted here by this dot, means it is entering inside this screen like that. Okay. So after it enters, after transmission, the we will call this component as ETS and HTS. So you can find their direction remains same. This is maintained same. This is also maintained same here. And one which is reflected back, one which is reflected back, its directions is reverse. So if this field was inward, now it will become outward. The direction of this component, again, it is maintained in the same direction. Okay, but it is only reverse. It is along X direction, but it is reversed. So after this, let us derive an expression. If you look at region 1, if you look at region 1, what are the different electric fields present? One is incident, another is reflected. If you look at region 2, there is the total electric field comprised of only transmitted component. The total magnetic field in region 1 is comprised of H incident and H reflected, whereas in region 2 it is only H transmitted. So let us, and we have already defined the waveform by E0 e raised to minus gamma z in the forward direction and e raised to plus gamma z in the reverse direction. So the total fields in the region, let us calculate the total field in the region. So what are these total? In region 1, E1 as total electric field in region 1, when it is propagating along Z direction, is incident plus reflected part of that, right? We have seen it. In region 1, incident plus reflected. Similarly, what is H field there? H1S is sum of HIS and HRS. Okay, HIS and HRS. Are you getting?
Yes, Miss, got it.
So EIS incident we will represent by EI0 e raised to minus gamma 1Z, and reverse we will indicate by ER0 e raised to plus gamma 1Z. Both are in medium 1, so we have written gamma 1 over here. Okay, and we have considered that E field is propagating in X direction, that is why AX bar we wrote here, indicating the direction. Now look at the H field, same thing. It is sum of the incident H field and reflected component of H field. What is the relation between E and H? I told you that you can relate H with the current, E with the voltage. Okay, so you know the current is equal to, or according to Ohm's law, V is equal to IR. It means you can write E is equal to I, voltage in is your field, current is given in term of H, and resistance we have defined intrinsic impedance by eta. Okay, so you can write E is equal to eta H. Okay, so therefore you can write H in terms of E as E upon eta. Okay, so you can write this H as E upon eta. So look at the second equation. This H we are writing in terms of E. So HIS can be written as, HIS means incident part of magnetic field. So that is equal to incident part of electric field divided by eta 1 into e raised to minus gamma 1 Z. Clear?
Yes, Miss.
Omkar?
Yes, ma'am.
So only we have converted this in the form of E. Now what is the direction we have assumed? Y direction. That is why we have written X. So E field is in the X direction, H field is in the Y direction. This we wrote for region 1, you can write it for region 2. So what it will be for region 2? The total electric field is only one, that is transmitted part. So E to S is equal to ETS, right? And you can represent is ETS as, you can represent this ETS as ET0 e raised to minus gamma 2Z, because region 2 is specified by gamma 2. So it will be ET0 e raised to minus gamma 2Z. Remember, this is the amplitude, maximum amplitude in AX direction. Similarly, you can write this H in terms of E. So transmitted component of H will become equal to ET0 upon eta 2 into e raised to minus gamma 2Z in AY direction. Now, as we have we have applied the boundary conditions. Let us consider Z equal to 0 position. Our waveform is moving in the Z direction, so let us consider the origin Z equal to 0. So when you substitute the value of Z equal to 0, this is Z. Everywhere you'll find this is Z. So what will happen if you make Z equal to 0? It will be e raised to 0 will become 1. So what is left? Even as everywhere. Even s at 0. So we will write this even s. We have made z equal to 0. So this term will become 0. This term will become 0. So you have only ei0 plus er0. So e1s is equal to ei0 plus er0. Similarly, h1s is equal to hi0 minus HR0. Now, why this is, yeah, one thing. This is a reflected wave. Okay, you see here minus sign up here. Okay, so for a reflection wave, direction is opposite. Okay, so when in transmission line we will derive the impedance equation for the characteristics impedance. There you will find for the reflected part you get a minus sign. Okay, so here you remember that here for the reflected component you have minus sign for this. Okay, so therefore this minus sign appears here. Okay, so you make the substitution of z equal to 0. Once you make substitution z equal to 0, you will get these two equations. Similarly, you can have this substitution for in region 2. Okay, so you get ET0 equal to, there is only transmitted part, so E2s at z equal to 0 become ET0, and H2s at z equal to 0 become HT0 upon eta 2. Pradeep Sadure, why you joined? You are not speaking anything. No reply. Now, so you get this equation. Now you know the boundary conditions. At boundary condition, this is the two dielectric. So according to boundary condition, the tangential component of E field and H field are continuous. It means ET1 equal to ET2 and HT1 equal to HT2. Okay. So we apply this. So our E1S, which is EI, yeah. Now here I'll use so you see here the incident portion E1S is equal to incident plus reflected part of E. It is EI plus ER at Z equal to 0. This is your E10. And similarly, this is incident and reflected part in terms of E for H1. Now you can perform you can solve the two simultaneous equation. We will consider now second equation, this equation. These two equation you have. Now let's consider this equation in terms of H. HT1 equal to HT2. Transmitted, the tangential component of H is equal to tangential component is continuous. It means HT1 is equal to HT2. So what was your HT1? So HT1 was transmitted. So this component and this component are equal. It means this equation. This is your incident and this is your this is in region 1 and this is in region 2. So HT1 was this in region 1, that is H1S, and H2S was this. Okay, so we will equate both equation, this equation and this equation. I'll use the whiteboard. Let's see. EI, and I'll call this as EI. Okay, we are considering Z equal to 0. So this is EI upon eta 1 minus ER upon eta 1 equal to ET upon eta 2, because I have used one direct step. So I'll rewrite this equation is EI upon eta 1 minus ER upon eta 2 is equal to ET upon eta 2. This is eta
Eta
1,
1 आहे का?
eta 1. Okay, good. So let's take this eta 1 common. So this will be EI minus ER is equal to ET upon eta 2. So from this I can write EI minus ER and not allow anyone to enter. EI minus ER is equal to, so I'll take this eta here, so it will be eta 1 upon eta 2 into ET. Okay. So we have this EI minus ER, and previously in region 1, if you look at this, this is EI incident plus reflected. Okay. EI plus E0. So your transmitted part, look here, the transmitted part, look at the cursor, ET equal to EI plus E0. So we will use this equation and we will use this equation. So from this equation, I have converted in the form of E, and we have already the equation for transmitted wave. So I will write that this is 2, and we have 1 as EI plus ER equal to ET. Now if you solve these two simultaneous equation, if you solve these two simultaneous equation, let's put it EI plus ER equal to ET, and EI minus ER, we will complete this, equal to eta 1 by eta 2 ET. So if you solve this, you will get 2 EI. Solve this two simultaneous equation is equal to, so ET plus eta 1 plus eta 2 ET. So ET can be taken common, then it will be 1 plus eta 1 upon eta 2. Therefore, you can have this ET is equal to 2 EI into, this will be eta 2 plus eta 1 upon eta 2. So it will become 2 eta 2, not 2 eta, this will become eta 2 upon eta 1 plus eta 2. Okay. Now, if I arrange this, Et upon Ei. What is Et? Transmitted electric field. What is Ei? Incident electric field. So this ratio is called as transmission coefficient.
मॅम
Transmission
ते eta 2 अपॉन eta 2 प्लस eta 2 कसं आलं?
eta 2 upon eta 1 plus eta 2. This is 1. This is 1. Solve this bracket. What this will be? Eta 2 plus eta 1. Eta 2 plus eta 1 upon eta 2. Okay. Then I have taken the here eta. Et आहे transmitted. You can add one more step here. This is Ei. Ei आहे divided by, or let's say 2 Ei divided by Et is equal to what? Just solve this bracket. Eta 1 plus eta 2 upon eta 2. Now what will be this ratio? Reverse the ratio. It will be Et upon 2 Ei equal to eta 2 by eta 1 plus eta 2. So transmitted E field upon incident E field is equal to 2 eta 2 upon eta 1 plus eta 2 Et by Ei ratio. Here also I am trying to find Et by, I have taken here only, I have written here in the form of T. I have taken here T. इथे Ei होता तर मी Et च्या फॉर्म मध्ये लिहिले directly. So you can do like this and then you can write the ratio like it will be 2 eta 2 upon eta 1 plus eta 2. Got it, Omkar?
Yes, ma'am.
Now see this ratio. We have to define two important ratio. One is reflection coefficient, another is transmission coefficient. So the ratio of transmitted to incident power or field is called as transmission coefficient, and it is equal to 2 eta 2 upon eta 1 plus eta 2. What is these eta 1 and 2? These are the intrinsic impedances of the media 1 and 2. Similarly, if you solve this simultaneous equation, like if you subtract 1 and 2, so what you get is, I will write this now. You, in the same fashion, you can find the ratio of reflected to incident electric fields. Okay, and we call it as the reflection coefficient indicated by tau. The previous was transmission coefficient. This is reflected coefficient. Reflected coefficient means reflected, you can say reflected voltage upon incident voltage or reflected power upon incident power. किती रिफ्लेक्शन झालेलं आहे ते रिफ्लेक्शन कोएफिशिएंट वरून लक्षात येईल. किती ट्रान्समिशन झाले हे ट्रान्समिशन कोएफिशिएंट वरून लक्षात येईल. So you can have, you will get, you try to solve this as eta 2 minus eta 1 upon eta 2 plus eta 1. Okay, so now what is tau? Tau indicates the reflection coefficient. Okay. If tau is equal to 0, reflection coefficient is 0, means what? This indicate that Er by Ei equal to 0. What does it mean? And tau is equal to 1. It means Er by Ei equal to 1. That means Er is equal to Ei. What does it mean? Now you will tell me its meaning in next lecture. Okay. Reflection coefficient 0 आहे किंवा ट्रान्समिशन कोएफिशिएंट 0 आहे. रिफ्लेक्शन कोएफिशिएंट 1 आहे किंवा ट्रान्समिशन कोएफिशिएंट 1 आहे. याचा अर्थ पॉवर रिफ्लेक्शन्स किती होत आहे that you will tell me. So this is all about the oblique in, sorry, normal incidence of plane wave. Okay, so we'll stop here.
सेम होईल ना मॅम पॉवर रिफ्लेक्शन?
किती कशामध्ये? इन when Er equal to Et, याचा अर्थ काय? रिफ्लेक्टेड in let's talk in term of power. So reflected power is equal to Incident power म्हणजे काय झालं? Means what
सेम झालं
happened?
मॅम. इन्सिडेंट पण सेम
Whatever
असेल
was
आणि रिफ्लेक्टेड पण सेम
transmitted,
पॉवर.
म्हणजे जेवढं तुम्ही ट्रान्समिट केलं होतं ते सगळं रिफ्लेक्ट झालं. म्हणजे लोडला काय मिळालं? शेटे नंबर सांगा.
38.
38. पवार.
32.
ओके, नथिंग इज डिलिव्हर. रिफ्लेक्शन कोइफिशियंट 0 आहे म्हणजे काय? रिफ्लेक्शन कोइफिशियंट 0 आहे म्हणजे काय? जसं आता रिफ्लेक्शन कोइफिशियंट 1, इट कॅन व्हॅरी फ्रॉम 0 to 1. Okay, it indicates how much power is reflected back. Okay. So these things you will be able to visualize properly in the unit of transmission line. Fine. I have submitted the attendance. 2 students only have marked attention because I don't want the people only to log in and listen and do not share anything. So unless and until you discuss, this is, I have already told you that this is a very tough subject, mathematical subject. So you must interact. So once, two, twice, thrice is okay, but always keeping quiet. At least you should tell me that I'm not getting, it is difficult to understand. Please repeat. Something must come from you. So fine, you can leave the meeting.